Hello, and welcome to AMAT362, Probability for Statistics at UAlbany. This is Lecture 13. Last time we just talked about some of the basic definitions of standard deviation and variance, and we really tried to get at this idea of where does this notion of variance come from? And we looked at optimizing decision-making where a penalty was governed by some sort of distance from the mean or the true value squared. Today, we're going to expand upon this idea and introduce the fundamental concept of tail probabilities, which essentially governs how rare events are. Now, to really motivate today's topic, I want to ask you the following basic question. If I were here in person with you, I would love to solicit answers from the audience just to see what people think. And but the question is essentially this: why are we impressed by tall people? All right, so this is the motivating question. And maybe you're not impressed by tall people, but I would assert that everyone has this like sense of when they see someone really tall, there's like a part of them that kind of goes like, oh, wow. Where does this wow factor come from? Well, fundamentally, it comes from the answer being that even just the definition of being tall is the idea that they're unusual or they're rare, or that they're tall when compared to the average. Let's try to drill down and understand what exactly we mean by this statement that someone's tall, or that seeing a tall person is rare. And this provides a good opportunity for introducing one of our first continuous distributions of a quantity governed by a random variable, namely things like height and weight, or even more controversially, this notion of IQ or intelligence. Of course, that being sort of a multidimensional thing, probably not summarized by a single number so well. But the basic idea is that height, like many things, follows a normal distribution. Now, you may have heard some other synonyms for a normal distribution. Sometimes you'll hear a Gaussian, or even a bell curve. And that's because when you look at the probability distribution, so meaning the function which sort of governs how likely a certain event is, such as like someone living in a certain range of heights, it's governed by finding the area under the curve of this curve, which has an explicit description as y equals e to the minus x minus mu squared divided by 2 sigma squared, all divided by sigma times the square root of 2 pi. This particular equation is so famous that it often gets the name of phi mu sigma. Or in the case where mu is equal to 0 and sigma is equal to 1, sometimes people just call this phi of z. I'm going to go ahead and instead write this as over here as just f of x. And notice here that I'm using a subscript x, which is meant to indicate that this is going to be a function that's kind of like a probability mass function, but for something that is governing a continuously varying quantity. But just to sort of highlight a few more features of this curve, this value here, which happens to coincide with the peak of this curve, is the value associated to mu, or the average. So this is a situation in which the mean, median, and mode all are the same thing in this particular setting. Again, in general, they're different, but in this case, they end up being the same. If I look at one standard deviation above and below, then I'm going to be looking at the area between these two values, and that's going to govern the probability of that event, which I'm going to tell you a little bit more about. But I'm going to go ahead and tick off a few more important special cases. So here we look at mu plus 2 sigma, and then mu plus 3 sigma, which is going to be way, way, way down here. Of course, what is mu and what is sigma? This is going to be the mean of our normally distributed random variable. And sigma is going to be, of course, the standard deviation, which we know is the square root of sigma squared, which is the variance. Now, something we're going to be focusing on in a few more lectures' time, as we transition to the theory of continuous probability, there's the following general rule for how to understand or treat continuously varying events that are random. Namely, so the rule for computing probabilities when X is a continuous random variable is this. The probability that I have an event that lands between values A and B is governed not by summing up all the possibilities between A and B, because in this case, there being continuously many, there are uncountably many, but instead I integrate this function, f of x, little x dx, where this right here we think of as the probability density function. Probability and you should compare this with the notion of the probability mass function, so PDF versus PMF. Now, in this case, when we're looking at a quantity such as height, which again gets at this question of why are we impressed by tall people, this function f of x for this particular type of random variable is this special function phi mu sigma, which is given by this e to the minus x minus mu squared divided by 2 sigma squared. That's up in the exponent here. And then I divide that entire quantity by sigma square root of 2 pi. All right, so let's ask ourselves, well, how would we actually compute? Let's say we see a tall person, and in this case, for us, a tall person is going to be, oh, I don't know, somewhere here. When we talk about this being a rare event, what we're saying is that if we saw someone of that height or greater, that seems very improbable. So in particular, we're interested in computing the area under the curve to the right of this value. Unfortunately, when we're looking at this particular function here, it's almost impossible to integrate this in the way you normally would in calculus. And there are sort of deep mathematical reasons why that's true. Nevertheless, because this is such an important function, people have spent a lot of time approximating, computing these huge tables of these values. And these are things known as z-tables. So I'm going to go ahead and just show you briefly what these z-tables look like. These entries are essentially telling us the area under the curve, let's say to the left, depending on various values of z, which you can think of as x, but z is going to mean something specific in our case. What we're going to be interested in terms of this right upper tail probability is going to be something that sort of corresponds to 1 minus one of these values. All right, returning to the notes here, let me go ahead and introduce some special conventions and write down what I just said. So unfortunately, for normally distributed random variables like height, this integral is impossible to compute exactly. Which goes really to the statement that this function back over here, this e to the minus x minus mu squared divided by 2 sigma squared, doesn't have a antiderivative that's expressible in terms of what are called elementary functions, things like sine and cosine and polynomials. But nevertheless, there are some really nice conventions, and this might get at the core of what colloquially or more sort of conventionally we talk about when we say something is rare, or unusual, or remarkable. Specifically, we have something called the 68, 95, 99.7 rule. And what this essentially says is that when I look at the probability of an event that lands somewhere between -1 standard deviation below the mean and 1 standard deviation above the mean, so written this way, so the probability that x is between mu minus sigma and x and mu plus sigma is approximately 68%. And if I look at the probability that mu minus 2 sigma x, this accounts for mu plus 2 sigma is 95%. And finally, the probability that x lies between 3 standard deviations above and below the mean, that is something that accounts for 99.7% of the time. Again, this is something that's only true for normally distributed x. So for normally we have, and where mu and sigma are again the mean and standard deviation of x. So mu equals e of x and sigma equals standard deviation of x. Now, when I was talking about this notion of an event being rare, I was using, in some sense, not that what we see most of the time, which is what really the 68, 95, 99.7 rule says. This really says that 68% of the time, you're going to see your random variable produce values that are within 1 standard deviation of the mean. So let me just sort of say that here. So 68% of the time, x will land within one standard deviation of mu, the mean. So that's the sort of English interpretation of this statement. And then correspondingly for 2 and 3 standard deviations. When I was talking about things that are rare, what I was really talking about is something called tail probabilities. And just to give you some language, when I talk about the probability that X exceeds some value C, what I'm talking about here is the upper tail probability. And this language sort of applies for any random variable X. But the picture here is that, suppose this is your PDF or your sort of histogram of values for X, then if I pick a value C, this is the probability that X is greater than C. It's sort of the area under the curve to the right of C. Or in the case of a discrete random variable, if I look at the histogram or my probability mass function table, I would pick a value C and then I'd sum up all the values that were larger than C and their probabilities. Similarly, if I talk about X lower than C, then here I'm talking about, maybe I'll call it D or B, how about that? This is the lower tail probability. I like the idea of using D. Lower probability. Maybe just for visual clarity, I'll say, all right, well, here's D. And suppose I want to know this area. Well, this is my lower tail probability. It's things to the left of D. Or if I were looking at a discrete random variable, I would take all the values up to, and, depending on whether this was a strict or not strict inequality, might include the value at D or not. So other bit of language which you all probably heard, maybe in an elementary stats class, such as AMAT 108 at UAlbany. If I talk about, let's say, X exceeding some value E, but where I take the absolute value, sometimes we call this a two-sided or a two-tail probability. But of course, the fact that we're using absolute values means that X needs to obtain negative values. So let's say, here's 0, and then I set as my threshold E. I'll use blue. Minus E plus C. I'm summing up this area, then that's my two-tail probability. Now, again, a lot of the random variables we've considered in this class, things like the binomial and geometric, these have been non-negative random variables. So this doesn't make sense, but it does if we usually apply this to the setting, not just X directly, but X minus its mean. So, because again, we're looking at what's the probability distribution of a value occurring either above or below the expected value mean. So usually we talk about probability of X minus mu exceeding some threshold value E. Because in that case, if we subtract some constant E or mu, then it's more likely that will have negative values, and thus this absolute value is going to be something that's interesting. So usually we make this 0 or mu, and then we look, and we're looking in this setting. So although it's pretty clear now that you can take your 68, 95, 99.7 rule and turn it into a statement about two-tailed probabilities, or even upper or lower tail probabilities. So let's go ahead and rephrase that a little bit. So again, in the situation, so let me call this the 68, 95, 99.7 rule, rephrased. We instead will say something like this, which is for a normally distributed X, probability of X minus mu exceeding 1 standard deviation, sigma. So let me just go ahead and make that open. X minus mu sigma is approximately, well, it's equal to 1 minus the probability that X is within 1 standard deviation. So it's the same thing as saying X minus mu is less than or equal to sigma. But we already said that this is about 68%. So consequently, this is approximately 32%. Sort of covering up that math a little bit more, then the probability of seeing a 2 sigma standard deviation or 2 sigma deviation is only something that happens about 5% of the time. And then seeing something that is larger than a 3 sigma deviation, this is something that happens only, well, 99.7 or 1 minus 99.7, which is about 0.3% of the time. Now, of course, these also translate into one tail or upper tail versions. So we look at the upper tail version of this. This could say something like, oh, well, the probability that X minus mu without the absolute value is greater than sigma is about half of 32%, so about 16%. And similarly, the probability that X minus mu is greater than 2 sigma is something that only happens about 2.5% of the time. And similarly, X minus mu greater than 3 sigma, something that happens only about 0.15% of the time. So nearly 0.1%. And the reason for this is, again, we have this sort of symmetry in the normal distribution, which is very nice. And in particular, if I look at this here, I'm looking at something like, this is a 1 standard deviation below. Then I have about 16% of the area below U minus sigma and 16% of the area above sigma, or together taken, those two tails would be 32%. So I think finally we're in a position to revisit the motivating question. So And this just uses some standard statistics about, let's say, the distribution of height amongst men and women in the United States. So for US men, so this means something like greater than 20 years old, we have the following. Mu equals 69.1 inches, and sigma equals something like 2.9 inches, or equivalently, 5'9", about 5'9", and about a 3-inch standard deviation. So what does this mean? This means that if you meet someone that's even 6 feet tall, so a 6 foot tall guy in the US is in the upper 16% of all men in the US. So in particular, when you meet someone or you see someone who's 6 feet tall, then you're sort of witnessing an event that only happens 16% of the time or less. Correspondingly, if we apply and all of this is essentially coming from the 68, 95, 99.7 rule. A 6'3" guy that corresponds to an event that happens only about 2.5% of the time. And a 6'6" guy, this is an event where the probability that's the probability of happening something like, well, that's a 3 standard deviation event. So so that's something, according to this calculation right here, happens only 0.15% of the time. All right, so almost less than 0.1%. I mean, a little more than 0.1%. This should really cause you to have some sense of awe or wonder. In particular, when we look at the pretty much any NBA player nowadays is in the upper 0.1%, I would say, 0.1%. I mean, we talk a lot in our society nowadays about the 1% in terms of the amount of money that people make. Sort of going along with that, you think about these NBA players. A lot of these guys are just by virtue of genetics and nutrition, something that's already in the top 0.1%. So they're sort of even more special in that sense, or rare. So this is a characterization of what it means to be rare. Just to provide a little more language, and not to scrunch it all onto a page, I'll just go ahead and call this. Here I started off with a statement about how much area was above or below a certain number of standard deviations, the mean for a normal random variable. More often than not, you get an observation, and then you need to figure out how rare it is using the mean and standard deviation. And this process is known as computing the z values, or standardization. So what this is a way of computing. So if we're given an observation, little x, produced from an experiment / random variable big X, then you can compute z, which is equal to little x minus mu divided by sigma. And what this is this is something that's measured in standard units. So this sometimes is called standardization. But essentially this measures number of standard deviations above or below the mean. Above, of course, if this is a positive number, and below if this is a negative number. So just as a quick example of how this comes up in practice, let's say you meet an adult woman in the US who's 5 feet tall. So a 5 foot tall woman in the US. Well, you need to know something about the distribution of women in the US. And the answer, I think this should be somewhat accurate, is that for women, the average height is something like 63.7 inches, which corresponds to 5 foot, 3.7 inches. And the standard deviation in height for women is about 2.5 inches. For men, I said it's about 2.9 or 3 inches. Yeah, here. So a 5 foot tall woman then has a corresponding Z value. So we have the corresponding Z value of 60 minus 63.7 divided by 2.5, which corresponds to Z equals minus 1.48. Now, suppose you want to know what's the probability of a woman being less than or equal to 5 feet tall. Well, by essentially subtracting the mean and dividing by the standard deviation, we can treat the normal distribution of women as being centered around 0 with standard deviation 1. So this is the same thing as saying that what I'll call capital Z is less than or equal to minus 1.48. And so I'll just go ahead and introduce this as Z equals capital X minus the mean of X divided by the standard deviation of X is the standardization of X. So this is essentially another random variable. But if you compute what's the mean and standard deviation of Z, you'll see that it's 0 and 1 respectively. And this process of standardizing it is then what allows us to just compute this table of integrals for just this single curve and use it to look up things. So here's where we then do our Z table lookup. All right, so I'm interested in finding what's the area under the curve when I look at, this is 0, this is minus 1.48. I'm trying to find this area right here. Well, if I navigate to that window I showed you earlier, you could see here, it tells me what the area under the curve is to the left of Z. But in order to use this table, what I need to do is look at the first 2 digits. So I'm looking at minus 1.4. All right, so this means that I'm in this row right here. And then if I go out to 8, I see that the area under the curve is 0.0694. So again, it's second to last entry as a column. And 2/3 of the way down here. So minus 1.48 corresponds to an area of 0.0694. So this tells me by using my z-table that this is a 0.0694 probability, which is to say that a 5-foot-tall woman is in the sort of lower 7% of all people. So that's a rare event, at least by some measurements of rare. It's not something you expect to see every day, or you would expect to see 7% of days, to put things somewhat differently. Now, this all is meant to sort of provide you with a quick refresher, maybe some elementary statistics and some of these skills. But again, in some sense, it's narrow in that it only applies to the normal distribution. So this process. So let me just. So this is what I'll call the standard normal distribution with mean equals 0 and standard deviation equals 1. And where people have computed this table of integrals. And again, these values were so important to science that and people didn't have computers back then, so people would literally print these sheets out, and you would compute by hand things like their z-value, and then you'd go look up what the probability is in one of these tables. Of course, nowadays we have calculators that can, almost everyone has a calculator, and it's not something we need to do. But what I was saying earlier was that this process is somewhat limited in the sense that all of this only applies to the case where I know my random variable has probability distribution that looks like this bell curve. So the limitations here, so is that we've only talked about rareness has only been quantified for events governed by a normal distribution. But in this class, we've been studying all sorts of examples of events where the distribution, let's say like rolling a die or flipping a coin, was governed by completely different events, such as the uniform distribution on 0 and 1 for my coin flip, or the uniform distribution from 1 to 6 for my die roll. Now, the good news is that we're going to actually soon see a theorem which says that normal distributions actually somehow are universal, in the sense that a lot of events end up producing distributions that end up looking normal. But it's still a good question to ask. Suppose you don't know what the distribution is. What can we say in general? And this ties back very tightly to the notion of standard deviation and variance for an arbitrary random variable. So what can we say for general so not just normal. How can we quantize this notion of rareness? Well, there are two inequalities which I want to tell you about. So we can quantify as follows. So the first thing is something known as Markov's inequality. And this essentially says that for a random variable x whose values are non-negative, the probability that x exceeds some fixed value, let's say c, so the upper tail probability, is bounded from above by the expectation of x divided by c. So the upper tail is bounded by expectation. So just to give you a quick example of how this is used, suppose there's a restaurant or a store or something, and we're told that on average they get about 1,000 customers a week. Example, a store gets on average 1,000 customers a week. What's the probability of them getting 1,400 or more customers in a given week? Well, we can apply Markov's inequality as follows. Well, we can't say exactly what the probability is. I mean, that would require doing a lot of inferential statistics, but if we just wanted a quick back of the envelope announcement or analysis, we could say something like this, which is that the probability that x is greater than or equal to 1,400 is bounded from above by 1,000 divided by 1,400, which works out to be about 71.4%. So that's just to let you know that, I mean, it certainly could occur, but the probability of it happening is less than 70%. Still sounds pretty good, but suppose you instead say, well, what about 2,000? So I have twice my average. Well, Markov's inequality would say it's less than a 50% chance of that happening. Or let's suppose I was really dreaming and 1,000 customers, maybe one week we get 10,000 customers. Well, that's something that would happen less than 1 out of 10 times. There's actually a much better inequality or bound that holds for general random variables. And this is called Chebyshev's inequality. And I love Chebyshev's inequality. It's so elegant and sort of maybe a little complicated to state and work with, but once you understand it, it gives you a really profound way of tethering notions of mean and standard deviation to this notion of rareness. And it says this, it's very, very straightforward. So for any random variable x, in the first part of the lecture, where everything we're assuming normal distributions. Again, this is for any random variable x, the probability of a deviation greater than c from the mean is bounded by sigma squared c squared. So let's continue our store example, and maybe let's go ahead and consider first of all this. So let's just consider exactly this situation. Suppose you're given extra information. So example, same store, where we know that mu is equal to 1,000 customers as above. But we're given some extra information, which is namely that sigma squared, which is our variance, is about 200 customers. Now there's a sense in which variance comes with units. They're kind of squared units, so that you'd almost say it's 200 squared customers, which is one of the reasons why we like to use standard deviation, which puts you back in the usual units. And the square root of 200 is, I think, something like 14 or something like this. Yeah, anyhow, yes, so sigma equals about 14. Yeah, so because 15 squared is 225, and so we're gotta be a little bit lower than that. Still not a huge standard deviation in terms of customers, but if we analyze the same question, well, what's the probability of X being greater than or equal to 1400? Well, we could certainly bound this by saying, well, it's less than the probability of having either 1400, which is 400 above the mean, or fewer than 600 customers. So said slightly differently, this is the same thing as saying that X minus 1,000 is greater than or equal to 400. Now, again, the difference here is in terms of distributions. If this was 1,000, up here we're considering 1,400 or more, but here we're going to consider both 1,400 and 600. So it includes both probabilities, but certainly the sum of those two blue areas is larger than just the red area. But anyhow, by Chebyshev, we would get that this is less than 200 divided by 400 squared, which is 1 out of 800, which is a very, very, very small percent of the time. So this just also shows you that, you know, Chebyshev's inequality beats the pants off of Markov's inequality, because we have this extra bit of information about what is the standard deviation. Let's do one more example related to this problem, just to get a sense of how that works. Here's another question. So suppose I want to know what's the probability that X lies between 950, where this is going to be the number of customers in a week, is between 950 and 1050. So again, with a little bit of, you know, massaging, you can see that, all right, if this is 1,000, this is 950, this is 1050, this is my mean mu. I'm trying to figure out this probability. Well, this is actually equal to the probability that X is between, so X minus 1,000, this deviation is less than 50. Now, notice Chebyshev's asked about things that go beyond. So actually what I wrote here was wrong. If I'm interested in this blue event, then this really corresponds to this area. But notice I can use the law of complements to get to what I want, which is that, well, this is the same thing as 1 minus the probability that x minus 1,000 is greater than 50. Oh yeah, sorry, I meant to have this as a strict inequality, and then this is the complement becomes a not strict inequality. But now I have something I can apply Chebyshev to, because again, Chebyshev asks for something that's a deviation from mu that's greater than c. And so now I'm looking for something that's greater than 50. Oh. Well, so this latter bit here, we know that minus, we know that probability of x minus 1,000, sorry, being greater than or equal to 50 is less than, so sigma squared, which was 200, and then I need to divide by 50 squared. That turns out to be 0.08. So we know then that the probability of 950 of our number of customers lying in this range has to be greater than 1 minus 0.08, just because the way these inequalities work when you multiply by a minus sign, which is 92% of the time. So more than 92% of the time, you're going to see your customers fall in the range of 950 to 1050. That's a pretty powerful observation if you want to start predicting how much inventory do I need and things like that. So the last application for today is essentially taking Chebyshev's inequality to look at sampling and what happens if we do an experiment multiple times. So this is a hugely important topic. So and it goes underneath the title of the law of averages. Or sometimes it's called the law of large numbers. And in words, this essentially says the following, which is that for large samples or a number of tries, the empirical mean will approximate the true mean. And again, we think of this empirical mean using x bar, the true mean, mu, almost certainly. So this essentially says that, like, if I have a coin and I want to determine if it's biased or not, then I could flip it a bunch of times and compute, well, how many times I get a heads, let's say out of 1,000 tosses. And I can now actually tell you exactly how close that is to the true mean if I'm willing to set, so let's say, a confidence level. To say it more mathematically in a way which you can then apply it to lots of different problems, the law of large numbers says this. So this is a theorem, and it says if x1, x2, all the way down through xn are IID random variables, that means independent and identically distributed random variables with, of course, e of xi equaling mu. And let's say the standard deviation of each of these xi's is equal to sigma. then the empirical mean or average random variable AN, which is going to be x1 through xn added together divided by n, is going to have the following bounds. Will satisfy for any epsilon greater than 0, probability of AN minus mu exceeding some threshold of tolerance epsilon. That probability is the probability that your empirical mean is more than epsilon units away from the true mean. That probability is bounded above by sigma squared times n epsilon squared. And you can get a sense that the proof of this essentially immediately comes from applying Chebyshev. Where you compute that the variance of AN is equal to the variance of x1 through xn divided by n. And then we use this independence assumption to turn this into n times sigma squared. And that factor of n in the denominator turns into an n squared. Let's go ahead and see how this problem or how this theorem is used in action. So obviously, if I roll a die, I could do it a bunch of times, write down the list of numbers, add them all up, divide by the number of times I rolled. So compute the average roll number. We know that theoretically the average should be 3.5. That's mu for the uniform distribution on 1 through 6. But it seems very unlikely we will actually get 3.5 on the nose. But how close will we get to 3.5? And suppose I wanted to guarantee that I'm within some number of that average. So here's the question. So how many times do I need to roll a fair 6-sided die to be within 1/2 of mu, which is equal to 7/2, 95% of the time? Well, what this answer boils down to is I'm trying to bound this probability. So I want the probability that my average roll is within 1/2. I want this probability to be larger than, so more than 95% of the time. Now I can again use Chebyshev, but first I need to apply this equivalent way of writing this. So saying that I'm within 1/2 would say something like, correspondingly, this is equivalent to saying that 1 minus this probability, AN minus mu, less than 1/2, is less than or equal to 1 minus 95.95. This just comes from multiplying both sides of this equation by minus. That flips the inequality, and then adding 1 to both sides. And then I recognize that by the law of complements, it's the same thing as the probability that AN minus mu is greater than or equal to 1/2. And of course, then I just write this down. This is less than 0.05. Now to finish off the calculation, I can now apply Chebyshev, or I can apply the law of large numbers. And I can say that, well, certainly if I bound this by some number involving n, and I can make that number less than 0.05, then I'll make this altogether less than 0.05. So what does that mean? So I have that probability of an minus mu greater than 1/2. Well, by Chebyshev's inequality is the same thing as sigma squared and 1/2 squared. And I want this to be less than 0.05. This ends up working out to being n greater than or equal to 234, where I am using the fact that for a 6-sided die, sigma squared is 35/12. All right, so we'll go through these sort of calculations in more detail in class as we go through our worksheet, but I look forward to seeing you all soon.